So in the last video, we finished talking about determining the areas between curves, or the areas in regions bounded by curves, when we were finding intersections to determine the bounds of integration. Well, now we are taking it to the next dimension, literally. We are going to be using rotation about axes to determine volumes of solid objects using integration. So this is where I would warn that Calculus 2 gets fairly tricky, and it's going to be fairly tricky for basically the rest of the course. That is how Calculus kind of is, but we hope that we'll be able to explain this in a fairly intuitive way. So we're going to be going pretty slowly through this topic because this is where most students start to have a little bit more trouble with some calculus. All right, so we're going to start off really easy just by defining what we mean by volumes by integration. So the intuition for a volume by integration in a single variable calculus frame basically thinks about we think about an axis here, and then we think about this kind of imaginary axis here. So this is the axis that kind of goes back into the PowerPoint. So the intuition here is that we have some sort of curve, right? We have some sort of curve like this, maybe. And where we start is we start by saying, okay, well, I know how to find the area between the curve and the y-axis, and finding it in the y-axis is just setting up an integral with respect to y, right? And we could also do this on the x-axis, but I'm drawing it upwards because I like to draw my volumes upwards like this. But basically, it says we can find this area here between 0 here, or it could be any starting point, and a height h. But then after that, what I could do is I could make an imaginary circle here, kind of like that. I could make an imaginary circle here, kind of like that. And then I'm left with kind of a reflection of my original curve. Then I can find the volume of this whole thing inside of here. So why is this important, and how do we do this? Well, this is important because it allows us to find volumes. It allows us to find volumes fairly easily with integration. And it also is allowed by the idea that we could have very small cross sections where the radius, because the radius here is different from the radius here. So we have very small little cross-sectional areas, right, with different radii that we add up as we go, and the radius is the function's distance away from the y-axis or the x-axis or whatever you're finding your volume about. So that's the basic idea. And this gets harder and more challenging, as we will see. Like at some point we might be finding the area in between curves, and then we rotate that around one of the axes, and then we find the volume of that washer shape. But we're going to keep it simple now, and I will just give you the formula right now. So if I want to find the volume, we have this Riemann sum that we can always rely on to give us rigorous definitions of anything involving integrals. So we say that the volume is equal to the limit as n approaches infinity of the sum from I equals 1 to n of A, the area of x sub I times delta x. Now, the area is the cross-section that I'm talking about. So this says basically if we sum up infinitely many cross-sections, which each model the curve that we were looking at, or the cylinder-ish thing that we were looking at perfectly, then we will get an accurate volume. And we can rewrite that as the volume being equal to the integral from a to b of a of x dx. All right, now everything I said there was probably pretty abstract sounding, so I would like to work on an example. And this example is going to be something that we could do through any number of methods, but I would like to do it through integration. And I put it all out here because I'm going to go fairly slowly through this, and I want everybody to be able to have a nice long look at it in its entirety. So this example is fairly easy. We're just going to be determining the volume of a cylinder with a radius of 5 and a height of 10 with integration. So we're going to do it with integration first, but then we are going to do it through our actual geometric formulas because we do have a geometric formula for the cylinder. Now, for calculus sake, I would like to do this through integration just so that we are able to see how this works. Now, something that's really important is that we draw a sketch. Drawing sketches was really helpful in our last mini unit of finding areas between curves. It told us where our bounds were, and that's going to be something that is extremely important when we are working in some 3 dimensions. All right, so we have a radius of 5 and a height of 10, and we're going to be integrating about the x-axis. I forgot to write that we were doing it about the x-axis, but we have x as our integration variable, so we're going to do it about x. In most problems, it will tell you what axis you were integrating about. All right, so we have our cylinder. So we have a radius of 5, so we're going to have 5 up here, and then we are going to have negative 5 down here. So that's negative 5. And our radius is that distance. So now we'll draw out our radius here. And that is our cylinder shape. Then we have a height of 10. So 10. So we go all the way out to 10. So we're going to be finding the volume of this guy. I don't think that was too bad of a drawing either. All right, so now that we have our drawing, we're ready to perform our integration. So first, what's important is that we find a of x. So what's a of x? Well, our function is really just the straight line here, right? This is y equals to 5 here. So we're really just going to be having our area being pi times r squared. And our radius is constantly 5. So that means that our a of x is going to be 25 pi. Now, this changes when I have a function that depends on x. Our function doesn't depend on x. Our function is just a straight line here. But if it did depend on x, we'd have an x in our a of x function. All right, so that means that the volume is going to be equal to the integral from 0 to 10 of a of x dx. So that's going to be equal to the integral from 0 to 10 of 25 pi dx. Now, this integral is going to be incredibly easy, I promise. Most of the integrals that we deal with in these volume videos are not going to be as simple. So the volume is going to be equal to now 25 pi times the integral between 0 and 10 of dx. So this can be really easy. That just means that our dx turns into an x. We get 25 pi times x evaluated between 0 and 10, obviously turning out to be 250 times pi. All right, now what we should look at is our formula for volume of a cylinder, which of course we know to be pi h times r squared. Or you could mix up the order of those variables. I don't really care. But you get v times pi hr squared. So we have pi times 10, which is our height, times 5, which is our radius. Then we square 5. That gives us, again, 250 times pi. So that means that our area here is 25 pi, and that our volume that we get in this big old cylinder is going to be 250 pi.